In the last video, we learned about camera transformations in the case where we can assume that the camera sensor is parallel to the plane that the camera is looking at. But in many practical situations, this is not true. I'm showing here an image that I captured by placing my camera at an angle looking at my board. In this picture, this is the x0, y0 position on the board, and what we're looking at is a bunch of squares that are each 1 centimeter by 1 centimeter, just like you have printed on your board. This kind of a case is more difficult than the other case we looked at in the last video, because as you'll notice in this picture, the pixel to centimeter conversion factor is different in different places on this board. And also, the pixel to centimeter conversion is not the same in the x direction as in the y direction. In other words, these are actually squares, but in this perspective, they look like rectangles. Now, if we know the angle of the board relative to the direction of view of the camera, and we also know the field of view of the camera, we could figure out the camera transformation analytically. But this is often not a practical solution because in practice, we often don't know for sure what is the angle of the plane that we're looking at relative to the direction of view of the camera. In this kind of a case, we can solve this problem using an empirical approach in which we create a mapping of the points that we see to the world coordinates. That's the solution that I'm going to show you how to do today. And we're going to do this using this specific example. So what we are going to solve today is we're going to find some equations that will allow us to take as input the pixel location of an object as identified by the camera, and it will output the x, y position of that object in units of centimeters in what we call world coordinates. That is, in the coordinate frame that is attached to the board in the world. Now, in the mapping process that we do in this video, I'm going to assume that the world is rotated around its own x-axis here, but it is not rotated around its y-axis. Or in other words, the camera is not tilted left and right, the camera is just tilted up and down. So to begin solving this problem, notice first of all that the pixel to centimeter conversion is maximum down here in the bottom of the screen, and it decreases as we get higher in the screen. This is true both for the vertical direction pixel to centimeter conversion as well as the horizontal pixel to centimeter conversion, although the value of the pixel to centimeter conversion is different in the up and down y direction than it is in the left to right x direction. Here's the order that we're going to use to solve this problem. I'm first going to create a mapping in the y direction to figure out the y position of the object in the base frame or in the world frame. Once we've figured out the y position of the object in the world frame, I will use that y position as input to figure out what is the pixel to centimeter conversion in the x direction, and then use that to find the x position. So I've opened this picture in Paint, and you'll notice that with my pencil tool, I can point to different places on the screen, and in the lower left-hand corner down here, it will tell me which pixel in the x direction and which pixel in the y direction I'm pointing at. I've also opened up Excel because this is what I'm going to use to record the data that we'll use to create this mapping. The first thing I want to do is find a mapping between the y pixel location and the y world location. I'll create a place in Excel to hold this information. So I'll merge these two cells together and say that this is our world coordinates, and I'll call this the X position and this the Y position. And then these are our camera coordinates, X and Y. Keep in mind that our world coordinates have units of centimeters, whereas our camera coordinates here have units of pixels. For this first part of the mapping, I only care about the Y position, so I want to capture some data where the X position is all zeros. And we'll get a couple of the Y positions, maybe 0, 2, 4, 6, and 8. So I'll position my pencil right at 0, 0. And I see that the pixel location of 0, 0 is 321, 468. Now I'll put my little pencil at 0, 2, 319, 342. And then at 0, 4, 321, 251. These numbers aren't exact, but that's okay because we'll be fitting this line, so it doesn't have to be exact. 0, 2, 4, here's 0, 6, 321, 185. And then 8, 0, 2, 4, 6, 8, 324, 132. Okay, now we want to plot this data. We want to be able to take as input some Y pixel value and produce as output a Y value in the world coordinates. So I want these numbers to be on the x-axis of my plot, and I want these numbers to be on the y-axis of my plot. Then I do insert. I want a scatter plot like that, and it swapped around the axes how I want them. Now I'll right-click on the data and click on Select Data, and then remove this series, and then add a new series, and select the X values. I want these to be the X values because that is going to be my input, and the Y values here. So here's the chart that I get out. I'm going to label these axes right away so we don't forget what we just plotted here. Okay, let's give a label to these axes so that we don't forget what we plotted here. Click on the chart, and then there's this little plus sign here. Let me slide this over so you can see what's happening. I click on the plus sign, and then I want to check axis titles like that. Then I'll have the titles show up here, and I can double click and then type in what I want here. This is the camera Y in units of pixels. This is the world coordinates y value in units of centimeters. Now click on the data and then right click on it and then select Add Trend Line. By default, it starts by giving you a linear trend line, but that actually doesn't fit our data very well. One way you can tell that is if we scroll down and we click Display Equation on Chart, and then we click Display R Squared Value. Let me drag this up here. The R squared value is only about 0.97. I would like to have at least 0.99 for my R squared value for a really good fit. So let's go back to the trend line. And instead of linear, let's do a polynomial fit of second order. And here we get an R squared of 0.999. So this is pretty good. I'm going to go with that. Now that we have this equation, we can use it to calculate the y position in centimeters, given the y position in pixels of an unknown position. So let's create a place to do that in our spreadsheet. Now, in our output cell, I'll hit equals. And I'm going to type in this equation right here. X is the y position in pixels. Let's test our equation. Suppose that we detect an object located right here. The y pixel value here is about 132, and the y position in world coordinates is 0, 1, 2, 3, 4, 5, 6, 7, 8. So we'll type in 132 and hit enter, and it tells us that our y position is 7.9. So that's pretty close to being correct. Now let's see if we can get the x position also. In order to get the x position, I need to keep track of what is the pixel to centimeter conversion in the x direction at different values of y. Now, let's start at the y value of 0. I'm going to look at the x pixel value. It's 320. Then I'll go look at the x pixel value over here, which is 489. Since that distance is 1 centimeter, if I take the difference between these two numbers of pixels, this is the pixel to centimeter conversion in the x direction at the y position 0. Now let's do it at 2. The center is still 320. And over here, it's 464. Let's do the same thing at 4. 443. And at 6. 429. And then at 8, 0, 2, 4, 6, 8. 419. Here I want to take as input the y position of the object and produce as the output the pixel to centimeter conversion in the x direction. So I'll select the y value and the pixel to centimeter values, and we'll insert a scatter plot. Let's add axis titles. Then click on the data, right-click, Add Trend Line. I'll scroll down to the bottom and check Display Equation on Chart and Display R² value. Now to use this value in our calculation, we need to do an intermediate calculation of the pixel to centimeter value. Remember that in our pixel to centimeter conversion, the input x is the y position in centimeters. Once we know the pixel to centimeter conversion at this particular y value, we can use that to calculate the x position. Since the 0x position is right in the center at pixel 320, to get the x position in centimeters, we take the x position in pixels, subtract 320, and then divide by the pixel per centimeter value. Let's test this equation. Suppose we detected an object right here. This is x equals 2 and y equals 6. The x pixel position is 536 and y is 182. And here it says that our position in world coordinates is 2 in x and 6 in y. So the calculation is pretty accurate. Now, before we conclude today, let me make a couple of notes about the usefulness of this approach to converting between camera coordinates and world coordinates in practice. In this example, we have a grid that was printed on a board that is positioned at an angle relative to the camera. But let's suppose that we were using this out in the world with a robot moving around a general unstructured environment. That environment probably doesn't have a grid already printed on it. However, suppose we gave our robot the ability to project a grid in front of it. The grid projected by the robot would also be distorted, not in the same way that this printed grid is distorted, but the distortion would be similar. We could then have the robot look at its own grid and automatically extract the data points that we extracted by hand in this video. And in that way, the robot could find its own conversion between camera coordinates and world coordinates, and in that way deduce the positions of objects around it in the world coordinates. This approach is known as a structured light approach, and it's the approach used by the Microsoft Kinect sensor and many other robotics applications that are out there in industry right now.